In our previous videos, we assumed an exponential distribution for the service time. That is, most of the service was quick and a handful took a long amount of time. But what if that's not a reasonable assumption for your organization? What if there is an average service time? So in providing whatever service it is, whether it is a call for support, maybe you're calling TELUS and you need help with your phone line or your internet, or whether you are waiting in line at the grocery store. Maybe it's not an exponential distribution. Maybe it's actually an average with a standard deviation. So the typical customer has how long that it takes for them to check out or to get the support they need. And then perhaps that it is distributed from there in more of a normal type distribution, where we can look at the standard deviation. Now, if you don't know the standard deviation, then what you can do is estimate the standard deviation by taking the maximum amount of time that the service takes, the minimum amount of time the service takes, take max minus min to find the range, and then divide that by 6. So that will give you the standard deviation, and that's based on the empirical rule. The idea is that we have in the center of our normal distribution the average, and as we go out, 2 distributions in each direction, 3 distributions in each direction, when we get to the 3 distributions in each direction, that covers 99.7% of the data. And so if you go 3 standard deviations in each direction, that's 6 total. That'll cover the majority of your data, which is why you can estimate the standard deviation by taking max minus min, that finds your range, and then divide by 6. We'll get your standard deviations if you have a normal distribution. So let's suppose in this scenario that our server time is going to have more of a normal distribution. And so our formulas then need to have a sigma squared for our standard deviation, and we need a mu. All right, so we are going to then do these formulas. So we're going to look at how those formulas change. And again, we're not doing the math. We're not deriving these formulas from these distributions. Instead, we're just going to use them to help us make decisions. And so I'm just going to move my face around because I'm hiding formulas. And then I'll move my face back. So the probability that the system is idle, no one is in the queue, we are still going to have our Poisson for our arrival rate, our lambda, for the most common number in a particular time. But then we're going to have mu and sigma for looking at how quickly people are served. So mu is going to be the average number in terms of the service, and the sigma is going to be the standard deviation. So we'll use, just like we did before, I'm just going to go back in time quick here. So our arrival rate lambda is the average number of arrivals per time period. The service rate mu is the average number of units served per time period. So those are still the same. Mu is still the average number of units served per time period, but now we have a standard deviation. So probability the system is idle is 1 minus lambda divided by mu. Average number of units in the queue is going to be dependent on our arrival rate, our service rate, and the variability of that service rate, that's sigma squared there. The average number of units in the system is going to be dependent on the average number of units in the queue, plus measuring those being served. The average time spent in the queue waiting is going to be dependent on the average number of units in the system divided by the arrival rate. I'm just going to move my face up. The average time spent in the system waiting plus getting served is, of course, going to be the average time spent in the queue plus a measurement of the service time, which is 1 over mu. Probability the unit has to wait for service is lambda divided by mu. And so let's take these and let's go into Python and let's do those calculations and see what we come up with. All right, so to do these in Python, what we're doing here is we are going to do arbitrary service time. Again, you will find these in drstephpowers.github.io/BIA. under the simulation workbook here. Open that in Google Colab, save a copy so that you can edit it. We're going to import pandas as PD. Okay. In our formulas, we're going to first create a function. We'll call the single serve arb for arbitrary. And we have lambda, mu, and sigma. So the change here is that we now are assuming a normal distribution for that service time. And so we have our formulas. We are using pow to do sigma squared. That's what this pow is here in our calculations. And so we simply write out those formulas that are our different metrics, have our function return those. And remember, it's going to return them as a list, number, comma, number, comma, number. So we want to make sure is when we call that function, we tell it what we're outputting. So make sure this here matches what you have here. So you've provided the same labels to what you have inside of your function. So let's look at a scenario here where lambda equals 3 and mu equals 6. So let's say that for our particular company, let's say that we are able to help. Let's say we have 3 customers arrive per day who need our assistance, who need support. Our mu is the average number that we are able to support per day. So notice that if 3 arrive, we are able to service 6. So for the most part, we're able to keep up with the queue. But there is variability. So we can't help 6 people every day because sometimes people take longer, need more help. So we're going to assume sigma here is 1.5. And so this allows for a range. Remember, if mu is 6, then if we go 3, so 3 times 1.5 is, 4.5? So 6 minus 4.5, so we can see our lowest there, that's going to be the minimum time. And if we go the other direction, so 6 plus 4.5, 10.5, that's the fastest. So best case scenario, we can help 10.5 people per day. Worst case scenario, we're doing 6 minus 4.5. And so we're doing less than 2 people a day. Okay, so that's kind of the variability in the number of people we can help. All right, so what we're going to do is call our single serve arbitrary function. Our lambda, we gave it our mu, our sigma, so let's do that. And then let's take that output and turn it into a dictionary so we can give this nice little report here. So the probability of idle is going to be that P naught. And so we've given names to all these different values, which allows us to do a run here to show that the probability that we're going to be idle is 50%. The average units in the queue are 20.5. The average time in the queue is 6.8 days, right? Because that was our measurement, was days. And the average time in the total system was 7 days. The probability they have to wait is 50%. So we could see here, right? Because we can on average help 6 people and 3 people come in. So half the time we take care of everybody in the day they came in. They don't have to wait. And so half the time we're idle. But because there's variability and because some customers take longer, then the average time in the queue is actually much longer, 6.8, being skewed by some people who are taking way longer to need support.